is given by Valerie King. Can you share your screen? And it's about upper bounding the number of intercomponent edges in random k-out subgraphs with, I think, applications to communication complexity as well.
I'm not able to share my screen for some reason.
Okay, let me see. You should be able to. Oh, there it is.
Okay, good.
Very
okay.
good.
Is everything okay?
Yes, perfect. Please go ahead.
Okay, so I'm going to talk about random k-out subgraphs. And this is joint work with Jacob Holm and Mikkel Thorup from BARC, which is a group at University of Copenhagen, and Or Zamir, who's currently at Tel Aviv, and also Uri Zwick, who's at Tel Aviv. So I just want to talk about where the problem arose. I was thinking about communication on a distributed network and how much communication, what's the communication cost of either broadcasting or constructing a spanning tree in a distributed network. So where messages are passed along the edges in the network. And a natural algorithm for doing this is to do flooding, where one person sends to all their neighbors, and then the neighbors send to all their neighbors, and so on. And if you do that, and say you know your friends, but maybe not your friends' friends, so you just send to your friends, the question is how many bits need to be sent in total over all the edges, either to broadcast a message or determine the connected components of the graph. And here M will be the number of edges, N is the number of nodes. Okay, so flooding uses O of M messages, but you can see that many messages are redundant. So the question is there, so we know a randomized algorithm, a Monte Carlo algorithm to do this. Is there a deterministic algorithm which uses little O of M bits? And as far as I know, that's still not known. That's assuming a general algorithm. There are lower bounds known for restricted algorithms. So when we don't understand something, we turn to a simpler problem. So instead, we're looking at N nodes, M edges, and we have a single referee. And now each node knows its neighbors, and they can communicate to the referee. And we assume that each node can only send B bits to the referee, and there's no other communication. So in other words, each node knows its neighbors, sends B bits to the referee, and that's it. The referee has to figure out what the connected components of the graph are. So how large should B be? So in particular, we're assuming private randomness, and we asked ourselves, what if a node sends square root n of its edges, or all of its edges if it had fewer than square root n edges? So this led us down a rabbit hole, and this is how we ended up at the problem I'm going to talk about today, which is the random k-out subgraph. So a random k-out subgraph is created as follows. For each node, if its degree is greater than k, then k random incident edges to that node are selected. Else, if its degree is less than or equal to k, all its incident edges are selected. And an edge will be in the subgraph if it's selected by at least one of its endpoints. Okay? Now, we found that we got the name from and found out that there already was something called k-out random graphs. These were proposed by Stanislav Ulam in the Scottish book in the 1930s, the Scottish book being a book of mathematical problems that was actually written up in Poland at a cafe called the Scottish Cafe. Anyhow, Ulam came up with this problem. Let there be given n elements. This is a translation of what he wrote, persons, To each element, we attach k others among the given n at random. These are the friends of the given person. What is the probability that from every element, one can get to every other element through a chain of mutual friends? And here they're assuming a directed graph. And this problem, so this problem is really a version of our problem where you're looking at the complete directed graph and you're selecting out, and each node is selecting out k neighbors. Or alternatively, you're just looking at n nodes and each one is randomly selecting k neighbors.
Valerie,
So
do you want to take question in between or at the end?
Oh, sorry. I can take a question, but
Okay,
I'm not watching the chat room.
No, I will tell you.
Okay.
So it's Karthik Chandrasekaran asks if sampling is done with replacement or without replacement.
So in the way we're stating the problem, you're just picking k edges. So it's not a replacement. It's not, you can't pick the same edge again.
Right.
Okay.
Thanks.
Now this problem on the of k-out random graphs was studied in the 80s by Alan Fries and co-authors, and he mostly studied this idea, something like this, where each node picks a random set of other nodes as their neighbors. But he did talk about some random subgraphs of certain types of graphs. But until now, as far as we know, nobody has talked about random subgraphs of arbitrary graphs. So that's what we're talking about here. Okay, so we have a theorem. Let G prime be a random k-out subgraph of any graph G. For k omega log n, the expected number of intercomponent edges of G with respect to the components of G prime is O of n over k. So let me explain what I mean by that. If you generate a subgraph this way, where each node picks k neighbors, k neighbors, and we include edges if they've been picked by at least one of its endpoints, then the subgraph G prime contains components of the original, some components of the original graph. But between those components, there may be edges of the original graph, and we call those edges, which go between components of G prime, intercomponent edges. And we ask, how many intercomponent edges are there? What's the expected number of intercomponent edges? Okay, so that we find is O of n divided by k. All right, now we conjecture that this theorem is true for even a constant number, where k is a constant, but we don't know. We haven't shown that yet. Okay, now n over k is the best possible, and there are several ways to see that. Here's an example of showing where if you that the expected number of intercomponent edges is n over k. So here's a graph which consists of two cliques. Each clique has n over 2 nodes, and in between the cliques there are n over k nodes in each, which are connected to each other by a matching. Now, if a node which is incident to an edge, so if none of the edges in the matching are picked in the random graph, then all those edges are intercomponent edges, and the cost will be n over k. So what is the probability that a node actually picks one of the edges in the matching? Well, a node is incident to n over 2 minus 1 other nodes, and in addition the edge in the matching. So the probability it picks the edge in the matching is less than k divided by the total number of neighbors it has. And therefore, the probability that no edge in the matching is picked is, oops, sorry. Oh, I forgot I can use my mouse. So the probability that that one of the edges in the matching is picked by one of the nodes is k over the total number of neighbors it has. And the probability that no edge in the matching is picked is 1 minus that probability, And there are two n over k such nodes that can pick one of the edges in the matching. So this gives us the probability that none of these events happen, which is a constant. So the expected number of intercomponent edges is the number of edges in here times the probability that none of them are picked. So it's n over k. It's still omega n over k. So here's an example where we're given a graph, and the cost of the number of intercomponent edges is the expected number of intercomponent edges is n over k, is at least n over k. Okay, now another association we have with these kinds of graphs is the kind of model that someone like Karger uses, for example, where each edge is picked with probability p. So just in contrast, this is gives us a very different kind of result. So here's an example of a graph where you have a clique of size n over 2, and you have 8k cliques where the other nodes are equally partitioned among those cliques. So there are n over 16k nodes in each clique. Now in this case, the k-out model will pick roughly kn edges. Each node will pick k edges. And the theorem, our theorem tells us that O of n over k, there'll be O of n over k expected intercomponent edges. But if we look at what happens with this other model, we'll have to get the same number of edges in our random graph, we'll have to pick p to be equal to kn over m, and that will give us roughly kn edges. Now here m is roughly n squared over 8, so p will be less than 8k over n. And the probability that a node in one of these small cliques has degree 0 is the probability that it doesn't pick any of its neighbors in this clique, which is 1 minus p to the number of nodes in the clique, which again is a constant. Okay, so the expected number of isolated nodes in these small cliques will be a constant times n over 2. There are n over 2 nodes in these. So the number of intercomponent edges, for every time you have an isolated node in one of these cliques, you get n over 16k, roughly n over 16k intercomponent edges. So the total number of expected total number of intercomponent edges in this case is roughly a constant times the number of nodes here times n over 16k, which is n squared over, which is O of omega n squared over k. So this gives you a very different number, this kind of sampling where each edge is picked with a random probability which is not dependent on the degree of the node, gives a very different number of intercomponent edges than the other technique that we're talking about. Okay. So again, this is the theorem we're going to try to, I'm going to prove, and I'm going to sort of tell you something about the proof. G prime is a random k-out subgraph of any graph G. For k omega log n, the expected number of intercomponent edges is O of n divided by k. And the cost of G, we'll call that the number of intercomponent edges. Okay, so that will be how we measure the cost of this random graph. Now, this problem as I defined it is a version you might think of as exact k out. In other words, each node picks k edges incident to V. Another possibility is this other distribution, which in the paper we called it expected k over 2 out. That is where each edge incident to a node V is picked independently at random. So it's picked with a probability, in this, I'm going to consider a distribution where it's picked with a probability k over 2 divided by the degree of V. Okay, this will give us roughly k over 2 edges incident to each node, and expected k over 2 edges incident to each node. Now, the reason I'm picking this, talking about this distribution is that it's an easier distribution to work with. And that's the distribution I'm going to work with. Okay, now it works because we can work with this distribution, which I'm calling H, instead of the original distribution K, because of this little fact here, which is that for any K greater than C log n, the probability that the maximum degree of any node in the graph generated according to H, it's not going to exceed twice its expected degree. So its expected degree is K over 2. And because K is larger than C log n, using Chernoff bounds, we're not going to exceed twice the expected amount, except with very low probability. So we can bound the expected cost, essentially when it is less than or equal to K, the cost of this distribution is certainly no less than the cost of this distribution, of the original distribution. So we can bound the cost of the distribution we want to consider by the cost of this expected K over 2 out. So from now on, we're going to actually consider the cost of the H distribution rather than the cost of the original distribution we described. Okay, so all right, so now we have the problem of bounding the cost of these meaning the number of intercomponent edges of a graph generated according to this H distribution. Okay, so let me just talk to you a little bit about how we do this. Let me just check time. Oh, okay, well, we started late, so I have a bit of time. I'm going to try to give you a sense of
take 15 minutes or so.
Yeah, okay. So the graph is, G prime is the subgraph. It's the random subgraph that we've constructed. But we're going to act as if it's constructed sequentially. We're going to be sampling edges incident to each node independently at random with different probabilities at different times. But with high probability, these probabilities are never going to add up to greater than K over 2 divided by the degree of V for each edge sampled that's incident to V. Okay, so, and there's one more thing we're going to do. As we grow we're going to grow G prime, and as we grow G prime, we're going to fix some edges. And what does it mean to fix an edge? We're going to say it's a possible intercomponent edge and it will no longer be sampled. So we'll count it in the cost of G prime. And I'm going to use the abbreviation UN, UN in green, to mean edges that have not been fixed. Sorry, I don't have COVID, I have an allergy or something. Okay, so there's going to be growing steps. We're going to try to grow G prime using thinking about the smallest components so far in G prime. So the smallest components will be called A's, A0, A1, A2, and so on. And notice, because it's the smallest component, when it finds an outgoing edge, it doubles in size. So it can't double more than log n times. And we're also going to have a trimming step where we fix edges in G incident to a node V. And we do that in two cases, but one case is when the undegree, the unsampled edges incident to V gets too small. When they get to less than 1/3 of degree of V, then we fix them. And notice that when we fix an edge, it has the effect of fixing the other endpoint, right? Because the edge gets fixed. So this may cascade, in fact. It will also reduce the undegree of other nodes. So you have to take that into account.
Would you mind having a question from a while back? Sorry. So Yossi asks whether you have these two different distributions and you said one kind of bounds the other, but do you know if there's a gap between them?
Well, there's a problem. There's a problem when K gets smaller, like less than C log n. Then we can't really make this case. So I don't know if, I assume that things will get very different when K gets small. And I actually don't remember if we thought about it explicitly, but it will be a problem. Okay, so there should be a gap. There should be a gap. All right. So in these growing steps, we talk about two kinds of growing steps, high degree and low degree. So if the smallest component contains a node V, whose undegree is very large, so one node whose undegree is larger than twice the size of the component, then we can sample edges out of this particular node until we find an outgoing edge. Okay, and that's going to work with high probability. The other case is low degree. That is, there is no node whose undegree is high, in which case we're going to sample edges out of each V and A in a way that I'll describe later. And if that fails, we're going to fix all the outgoing edges from A and G. So all the edges coming out of A will be assumed to be intercomponent edges, and we'll just add them to the cost. All right. So, and then we'll continue this. This is all we do. We continue this until there are no more unfixed outgoing edges in G. Okay. And now we can show that the number of edges fixed by the trimming step is no more than the number of edges, O of the number of edges fixed by the growing steps. I'm not going to say why, and I'm just going to keep going. It's not a difficult point. Okay, so it remains to show two things. One, that the expected number of edges fixed in the growing step is O of n over k. And two, that when we do what we're going to do, the probability that an edge is sampled is from V is k over 2, k divided by the 2 times the degree of V, because we want it to be one of these in this model. Okay. And I just want to point out, it suffices to show that the sum of the probabilities for an edge being sampled is O of this quantity here, because then you still get the result of O of n over k prime for this new k. So it suffices just to show this for O of this amount. Okay, so the high degree case is relatively straightforward, and I pretty much said what it is. If half of the edges are going out or outgoing edges, then when you randomly sample those edges, and remember k is, if you do k over 2 samples, and k is c log n for a large enough c, you're going to have a high probability of success of finding an edge that goes out. And in fact, you'll have a high probability of having log n successes. In other words, for every time a node plays this role in some A, and it's only going to be in most log n A's, it's going to have high probability of success. All right, so that brings us to the second case, the low degree case. All right, so now we assume that all the nodes in V have a low undegree, which is less than 2 of the size of the smallest component that it's in. Now we're going to sample each edge incident to any V and A with this probability. Okay, so what you're seeing here is k times some c divided by the size of the undegree and the size of the of A, and all taken to the square root of this. So then we need to show two things. One, that we're not going to sample an edge with too much probability over the course of this construction. And two, that we're not going to fix too many edges. Okay, so the probability that an edge is sampled by its endpoint, from the point of view of its endpoint, is just the sum of these probabilities. But notice, because we have this A in here, and the A's are growing, then it's dominated by just putting in the original A and having this extra factor, which is growing by, the A's are growing by a half, so this is getting divided by 2, and it's the square root of this. So we can just take this out. And when we do that, it's given the constraints we have on the undegree and the size of A, then we get that this whole expression comes to O of k divided by the degree of V, which is what we wanted. So we've shown that each edge is sampled with no more than the right probability. Okay, now the second part we need to show is that there aren't too many the expected number of intercomponent edges is not too large. And I wish I could show you that, but it's kind of complicated. So instead, I'm going to show you that it's O of n over k log n. It's complicated. It has a lot of cases. I'm going to show you an easier version. It gives you a flavor of those cases. All right, so the way we show this is that we show that the number of edges fixed per node in A is less than log n over ck, over some constant times k. So what's going on? What we're trying to do is find an outgoing edge from A. And this is the boundary. We'll let this del be the boundary of A. We're trying to find one of these edges by sampling. And we're sampling each edge with this probability. Now we note that this probability is around k over the size of A. And the probability we fail to sample any of these edges is just 1 minus this probability raised to the number of edges, which is the size of the boundary. So therefore, the probability that we actually fix these edges, remember we fix these edges when we fail to find one of them, it's just the expected number of edges fixed is the size of the boundary, and then we take it per node, so the size of the boundary per node, times the probability that we fail to find any one of them, which it turns out to be 1 over ck. And when you consider that each node, so this is the value per node, this is the expected number of edges fixed per node, and every node appears in no more than log n A's. So this is log n over ck per node, and there are n nodes, so we get n over k times log n for all the nodes, multiplying pi n. So this is a bound on the expected number of edges that we'll need to fix. And I can't get further than this, other than to say that there are like very special cases that you can reason about to get rid of the log n factor. Okay, how much time do I have now?
Say 5 minutes.
Okay, 5 minutes. So we're back out of the rabbit hole, back to the problem that we started with. How large does B have to be if every node is sending to some referee? Now, it's not hard to see, or to come up with your own collection of edge names of length square root n log n, such that the bitwise XOR of those names of any subset of size square root n is unique. In other words, you can name every edge a name of length square root n log n, and if you take any subset of square root n of these edges, and you take the XOR, the bitwise XOR of those names, you'll get a unique vector. Okay, so with that, here's the algorithm. Each node sends a random sample of square root n of its edges to the referee. That takes log n bits per edge. And it sends the vector, which is the bitwise XOR of the names of all its incident edges, which is again square root n log n in length. So it's sending square root n log n bits to the referee. What does the referee do? Well, the referee takes a look at this k-out random graph that was sent to it. And we know that it has, there are only, by our theorem, there are only square root n, O of square root n intercomponent edges. So it can, by looking at the vectors and taking the XORs of all the vectors in any single component in the random k-out graph, it can determine all the edges leaving that component, because all the edges, all the intercomponent edges make up no more than square root n. So using this coding theory, it can take the XOR and uniquely figure out what the edges are leaving each component. So in that case, it can also figure out the connected components. All right, so that brings me to the open problems. The main conjecture is open for k, which is little o of log n. Now, I mean, Mikhail and Omer, Or and other people have been working on this. You may want to talk to them. And then, we can ask about other properties of k-out random subgraphs. Ghaffari uses random 2-out, Ghaffari et al. Uses random 2-out subgraphs for edge connectivity in a SOTA 2020 paper. And we can also come back to the one-way communication problem, we still don't know anything about the deterministic complexity of that problem. And we also don't know about the deterministic complexity of connectivity in a general distributed network where each node knows its neighbors. So we do know some things, and there is a lower bound of log to the 3n for B if there's public randomness. Okay, so thank you very much. It was really a pleasure to be invited here. Thank you.
Thank you
Any
very
questions?
much. If anybody has questions, please write them in the chat box, and
Oh,
I
I
will
wonder if I
read
can
them
see
out.
that now.
So Karthik asked, so you assume that K is at least order log n. This seems to be necessary to transition to this other distribution.
Right.
But it appears like you also need the assumption to analyze the age distribution. Is that true?
To analyze the which distribution?
The age distribution. I can only read what's written here.
wait. But you see, the thing is that there's like an infinite, there's like many, I'm leaving out a lot of the, there are ways that we can possibly get beyond the analysis without that. So yes, we did use that, but it's not clear that we need to use that.
Right. So
you're right. We would need something different. I mean, we used it for a reason because it made the analysis. It was a way to analyze it. Right.
So Yossi asks, you assume that the names of the edges are global for your algorithm?
Well, and if you wire into your algorithm the fact that you're going to use a particular coding method, so for example, I think some standard code, BCH, some standard coding tricks will work. Standard coding techniques will work. So every node knows what coding technique you're going to use, so it can name its node. It's not a random thing. It's a fixed code.
So I'm trying to. Okay, so follow-up question to the one about the distributions. So the age distribution can be analyzed without the assumption that K is at least order log n. Is that correct, or you're not sure?
Well, so what do you mean it can be analyzed without that assumption? Oh, you're saying, could I prove this for the H distribution without proving it for the other distribution?
I guess.
No, I don't think we can. I don't think we know how to do that.
I mean, there's a clarification.
So the question is, would it even be true for the H distribution?
Yes.
Okay. And I don't remember if we showed that or not. Yeah, I don't remember explicitly if we showed that it was false. I mean, I'd have to think about it. I'm guessing it wouldn't be, but I don't know.
So Ozamir says it wouldn't hold, but
okay, good. Okay. Thanks, Or.
Anyway, let me advertise the Slack once again, because there's actually some long discussions going on there and so on. So it's really being used, and so maybe it's interesting to continue those discussions. People are saying thank you for the answer to their questions.
Yeah, I see it. I see.
And thank you very much for the result and for the nice talk. Also to the other two speakers. I think that is it for today. Apologies that we're slightly late because we started late, but I hope people can live with that, and see you all back tomorrow.